Hi. Let me see if I can give a quick scan of the room. Um, at the dining room table, nothing too crazy. Um, yeah, just a blank sheet of paper. Yeah, front and back. Okay, so I'm gonna have to pan back and forth here to kind of show kind of what I'm doing on the paper, but the ultimate goal here is that we're going to be calculating the electric field at point P over a uniform electrically charged ring. So where we want to start with that is kind of drawing out a diagram real quick on just what that's going to look like. So we got our circle here, and then some things that we do know is that, yeah, we have point P that's hovering above, and then we have the distance above, which we will call that Z. And then we also know that we're gonna have a radius R of the ring below. We also know that this ring has charges all around it. So we're gonna just try to take one of those charges and we're gonna call that point DQ. Then let's see. Oh, we also have the distance between one of those points and R. I'll draw that here, and we'll just label that with a lowercase r. Okay, just a quick little setup. Sorry, it may not be the greatest drawing here. So what we're gonna need to do is we're gonna use Coulomb's law. So we have DE equals K Coulomb's constant. We have DQ, and then we have in the denominator we have R squared, little r squared, and then times R vector. Okay, there's that. You can see it, and then I'll kind of like show the whole thing at the end just to kind of walk through it at a high level. So another major point that we need to find out is that we're going to do those charges that are all around that ring. We're going to integrate so that we can find and add all of them up together and use that to calculate DE, or to calculate E. So we have E equals the integration of DE. And at that point, I'm just going to start doing what I can solve. So let's solve for little r. Little r will just be simple Pythagorean theorem. So we have r equals, it would be the square root of z squared plus big R squared. Oh, and then also one thing that's very important to notate here is that this was drawn specifically for a reason like this, right? So we have our XYZ plane, right? The X and the Y are the horizontal, are the horizontal components, the way that it's drawn out here, and the way that these DQs, they all have vectors, and they're pretty much all canceling each other out because it's symmetrical right down the middle. And since these horizontal components are symmetrical, they cancel each other out, leaving us with just the vertical component. So at that point, we can say that E is equal to DE cosine theta, because pretty much all we have is just the vertical components here. So yeah, I could have drawn this a little bit better, but yeah, so we have the X and Y is how this ring is drawn on, which only leaves, and those cancel out, and that only leaves, you know, our vertical component going up, or vertical. Okay, so back over here, so we know that also cosine theta would equal to z over r. And then we can just keep plugging, we can just keep plugging that in. So we know that, or we could just plug all this in to our original formula for Coulomb's law. So we have K dq, and now we do know what r is, little r. So we know that is z squared plus, or the square root of z squared plus r squared. However, in the original formula, it's squared, so that will take out the square root. And then we have times what is now cosine theta, which is represented by z over r. And then we can replace r with what we got with the square root, z squared plus r squared. So I'm just going to write that all out. Z over square root z squared plus r squared. Okay, combine those all together and make it look a little nicer. We will go K Z dq over, and then we'll just combine the denominator into one. We'll just say z squared plus r squared to the 3/2. All right. Yep. Okay, so this is kind of where we're at now. So basically now, one important thing to notice is that everything's a constant except for dq. So at this point, we're trying to integrate further, right? So we need to set this up in a way where we can set it up for integration. And one of the ways that you can do this for the disk is taking the arc length. What we would do here is dq. To find arc length, we know that dq equals lambda r d theta, right? And then we can just plug that right back into the equation. Oh, excuse me, sorry, I'm getting a little ahead of myself. Since we are going to be trying to integrate, we need to know our bounds as well. And since we are trying to integrate around the whole circle, we know that our bounds of theta are from 0 to 2 pi. Right? So now we can just set up the integration. We would have that E equals the integration and of that whole formula that we've been working with this whole time, kz, and instead of dq, we'll plug in the lambda r d theta, and then all over z squared plus r squared, and then 3/2. And then at this point, again, like I had, and then we also have to set our bounds at 0 to 2 pi. And then at this point, we're just taking the integral as I said, the earlier, most of these are constants. The only thing that isn't constant now is the d theta. So we can pull all those out of the integral and rewrite it as k z lambda r over z squared plus r squared to the 3/2. And then we still have the integral from 0 to 2 pi of d theta, which we know that once we integrate this out, this will just end up being 2 pi. So that's pretty much it. We can push 2 pi into the numerator, and then we are finished with, and we are left with k z 2 pi r over z squared plus r squared to the 3/2. Awesome. Sweet. This is kind of my work. I guess some major things I just kind of review and reflect is one thing that is a major importance is that this was only able to happen because we set it up in the way where the x and y components could be canceled out through their vectors, right? And then because of that, we were able to only look at the vertical component and use that cancellation to find the electric field at P. Awesome. Thank you so much. One last time, here's this guy, nothing on the back. I may have to flip this video just so this makes somewhat sense, but we'll deal with that later. Awesome. Thank you so much.